Hello everyone. Thank you for joining my master's thesis presentation today. My name is Pasi Pyrrö and I'm a master's student in Aalto University School of Science. I'm studying in master's program of Artificial Intelligence, Machine Learning and Data Science. Before we start, I should mention you that this presentation will be recorded, so keep that in mind if you don't want to show up on the video. And if you have any questions, please feel free to interrupt me anytime. Because I probably won't just notice if you raise your hands in Zoom. So raise your voice instead. Now back to the topic of this presentation, which is about aerial inspection RetinaNet, which is a computer vision solution for automatically detecting humans from aerial drone video to support land search and rescue missions. So here's the overview of this presentation. After giving you the introduction to this topic, I'll describe the problem and give you some background work, what has been done to solve it, and what are the key challenges. Then we'll discuss the important topic of solution evaluation, which means how do we rank different solutions to this problem. And that enables us to meaningfully compare solutions to each other, so we can determine which one is the best. Then there is the closely related topic to this is a bounding box aggregation, which means basically post-processing the output of an object detector that outputs bounding boxes. So it affects how the final results of the detection look like, and also it affects this evaluation. So it can affect even your score. How do you present the output boxes? And the last topic is about the experiments which have been done to come up with the solution. I'll give you the main results and describe the most important experiments. Then I'll conclude this thesis with the key contributions, what have been done during this thesis work. All right, so search and rescue missions have been carried out for decades to look for missing persons in the remote areas such as wilderness, some forests, and maybe mountain areas. And this is a long tradition, but only recently have these flying drones, which are remote controlled quadcopters basically, have been used to assist this search efforts in many countries and already many years. The reason for that is that you can take photographs from the air, and that you can scan the whole area with much faster than is possible with ground search teams. And also there's it doesn't matter how difficult the terrain is to traverse, so as long as you are just moving in the air. And these drones are typically equipped with high resolution cameras, so it's possible nowadays. And it's on one of the benefits is of course that you don't have to go travel by foot there in the forest yourself, so it's much safer to use this remote control drone so you don't fall off a cliff or something while searching. And then of course this is also much faster than traveling by foot, so in some ideal situation you can even achieve the benefit of several tens of ground search team members, so you are as efficient as that many ground search team members with one drone unit. But you're not done yet. If you just photograph the area, you also have to look through the video material produced during this flight, and it's usually done by humans, and they are looking for any clues about the missing person location. It can be the person itself, or it can be some item that person has dropped. But the problem is that there's just so much video material to look through, and it's quite slow and it's tedious, you can imagine. And after you have looked through a couple of hours of video, you might start to lose focus and start to make errors as well. So the problem of this thesis is how do we do this more efficiently? So how do we enable more efficient aerial drone searches in SAR? Well, this is a machine learning thesis, so we can try automating it with deep learning. So my idea is to train this object detector, which is based on well-known RetinaNet deep learning architecture, to solve the so-called aerial person detection problem, or short for APD. And in SAR context, it's called C-SAR-APD problem. That's the name I came up with for this. And it's a more specific version of aerial person detection problem. All of these are like instances of object detection problems. But this problem has some requirements for the image viewpoint, and also what labels there are, and then how accurate bounding box labels we need to output to consider them as valid. Of course, just taking this RetinaNet detector, even though it's very sophisticated and works well in practice, you still need to make some kind of modifications to it to account for this small object detection problem, and especially from aerial high-resolution images. So some modifications need to be done for it to be suitable for this problem. And that brings us to the outcome of this thesis, which is the aerial inspection RetinaNet, or in short, AIR. So it is the outcome of all these modifications and experiments conducted during this thesis, built on top of this RetinaNet. But first, let's define this C-SAR-APD problem. So here is an example image taken from air with a drone, and you can see that there is small humans present in this image, and most of is just background vegetation, trees, and all kind of stuff. But the goal is simply to locate the persons in this image and maybe denote their location with a bounding box. Somehow mark them on this image, on top of this image. And without this magnification here, it would take some time to scan through this image and actually spot the persons in it, especially if they weren't wearing so bright clothing like this guy here. And some of these might not even be humans, even if they are bright spots, although they can be useful clues nonetheless. But so as I mentioned, this is done by humans normally. But before we start to automate this with deep learning, it's useful to know how good are humans on average in this task. So we know that our solution is bringing some value to the table. To answer that question, I conducted this so-called meta-analysis study from 3 different studies that study this topic of how well humans can inspect through these images and how fast are they and how accurate they are. So there are 3 metrics listed: this precision, recall, and average time per image. And the interesting observation here is that the more you have to look through images, so here are 3 groups and their number of images they all needed to inspect, like per person. And the more images you have, the less accurate you get. And also you tend to spend less time for each image. So clearly some fatigue effect is here in place, I would presume. And by taking the weighted average of these metrics here, or plotted here, so you can come up with some sort of baseline for human performance. Of course, it's rough and it would not work in every situation, but at least it's something. We have some numbers that how precise, how much recall they achieve, and how much time are they taking per image. And 30 seconds per image is not the best, not the best results. So clearly we have some room for improvement here. So by the way, if you want to see all the details about this study, meta-analysis study, you can check section 2.2.2 in the thesis. All right, so we are decided to use machine learning. So usually some type of data set is involved whenever someone mentions machine learning. And in this thesis, we use Heridal, something called Heridal for this task. It's a, well, it is a data set that has only one person, and it's, I mean, only one class, which is the person, and the images are taken from this aerial perspective, and they are very high resolution, and the location is somewhere, some Mediterranean wilderness, different locations there. And currently there is no alternative data set publicly available for the same task, as far as I know. It has some almost little less than 2,000 annotated high resolution images, so it's could be more, but it's better than nothing. This is this problem is like quite not so much well widely studied, so there are many ad hoc solutions, not so much these so there are not well-known methods how to do this. So there are many kind of different approaches, and it's a difficult problem because of many variables in the problem. For example, like environment, angles, distances, like how the image was taken, and then of course the most notable one is the extremely small size of objects, which makes it difficult for object detection algorithms as well. Although you can somewhat exploit this natural background property, which is quite uniform, so you can, some of the bright spots are easily extractable from the image. So even some of the simplest methods, ad hoc methods, are to just threshold the image pixel values in some appropriate color space. There are obviously there are some limitations to these handcrafted rules that you can come up with, because there is a lot of variation in the terrain and what kind of lighting conditions it can be during night, but also during night they usually don't conduct these searches. But anyway, there are endless possibilities what the image can look like. So typically, to incorporate more of this inherent variance in the problem domain, you would like to use a machine learning solution to solve this C-SAR-APD problem. And there are many different ways. There are many, some of the works have been listed here. I don't go into too much details, but this item 2 is interesting from that point that it's using thermal imagery footage for the object detection algorithm. So the idea is that human thermal signature is different, or if they are radiating infrared radiation, so they could be easily extracted from that thermal image. But it turns out it's not a magic bullet that solves your every problem, because during summer the background can also emit enough radiation that you won't be able to distinguish the persons from the background. Then these two were like traditional methods, so to say, traditional machine learning methods to C-SAR-APD. Then there are 3 deep learning versions methods listed here. I will be actually comparing against these later when I'm talking about the experiments and the final results. And this work has been using heredal data, so it's kind of the benchmark in this area, this problem domain that people are using. Okay, so now we know what the problem is approximately, and then before we start to come up with a solution, it would be nice to know how to rank the correctness of the solution, like how well are we doing to solve the problem. And it turns out it can be ambiguous, like how to do. It's not self-evident how to rank the object detector performance in a multi-object scenario. And the basic idea is to match bounding boxes which are predicted by the object detector with the ground truth boxes, which are labels drawn by humans. They are part of the data set, the correct examples, so to say. So we try to match them somehow. So given that there is some overlap between the 2 boxes, so they are kind of on top of each other. And given that we successfully match prediction with a label, we think of it as a true positive detection, given this evaluation algorithm. And the rest are considered as false positives, which are true positives are like, you can think of them as plus points, and the false positives are minus points. These two numbers can be used to calculate the final metrics, such as precision, recall, and average precision, which are used typically to rank object detectors. That this is what people usually report. The average precision is the most popular one. It's because it combines this precision and recall in some meaningful manner. However, it's not clear how to do this matching. How much should there be overlap between the two boxes before we consider the prediction as true positives? And do we need each prediction? Do we need for each label, do we need one prediction, or can we group some of the labels inside one prediction? So think about group detection. Okay, well, one answer to this question is the traditional one, which is taken from this PASCAL VOC 2012 object detection challenge, which is widely used. Its approach to this evaluation is quite strict. So we require this 0.5 IOU or intersection over union metric. So 50% of the overlapping area has to be at least 50% of the union area between the two boxes. I'll show you an example later, but this is another requirement here is that you need one-to-one mapping between the predicted box and the label. So there needs to be exactly one prediction for each label to get the perfect score. The problem with the strict alignment requirement is that this is not designed for very small objects, and with the small objects, it tends to be really difficult to actually fulfill this requirement. And the second one is that it turns out this heritable dataset is filled with these dense person groups for one reason or another, and separating these small person groups so that each person label has its own prediction is quite intimidating task for this C-SAR-APD setting. So we identified that this is a major bottleneck which is limiting the performance of object detection solutions on heritable test set. And the funny thing is that it's not even that relevant to the real world SAR requirements. If we just get the location of the group, then we are sending someone there who can count the number of those persons as well. So the idea in SAR RL search is to produce a rough georeference so that we can about the clues about the missing person. So, and it doesn't have to be like within 1 meter, it can be even tens of meters accuracy on the ground. And anyway, someone is going to go there by foot and go check whether the evidence was correct or not, and possibly rescue the person if it was found. So then can we do this evaluation somewhat differently to incorporate these problem-specific requirements into it so that we get better signals about the object detector performance, which align with the real-world objective. So in this thesis, I proposed this C-SAR-APD evaluation, and the first thing we changed from this VOC 2012 is that we relaxed this alignment requirement significantly, so it's much lower, much less overlap is required. And this also means that there is you can also output much larger boxes than just aligning, and you can even output so large boxes that are about 2 20 by 20 meters on the ground. And if the person is inside that box, we still consider it as true positive. This, of course, assumes some flight altitude and the camera characteristics, but this is like some rough number here. And the second thing is that we allow object grouping, so many labels can be matched to a single predicted box. So we don't need to, well, here's an actually good picture for that. So we don't need to separate these blue ground truth labels, every one of them having a separate red prediction box, but we can just group them inside one big prediction box. And this, using the C-SAR-APD evaluation, this would be like perfect score. You would get all the points you can possibly get. But using the VOC 2012 evaluation, you would get 0 points. There are like 5 false negatives, and this one would be considered as false positive because it's too large to fulfill the IOU criterion with any of these ground truth labels. And then you can, of course, attempt this delineation of each individual object, but it can be intimidating problem because the objects are small. But this is actually large magnification, so they don't look like this big in the whole image if you are looking at it. So okay, so we discussed how to evaluate these predicted boxes, but how do we then come up with the predicted boxes? If we don't do something called bounding box aggregation, this is what the output boxes look like, this A figure here. Because there is a reason for that, because of this sliding window property, and we are usually considering many adjacent locations per image, and they all can trigger this positive class detection. And so we need something like bounding box aggregation to get rid of most of this clutter here, the duplicate detections. And well, we don't actually even see the persons here if we just use this, although we would get the rough georeference. But for visualization's sake, we would prefer this C version likely to the other options here. And there are, okay, in this thesis we consider 2 ways to do this. But before let's consider what is bounding box aggregation. So these duplicate detections are not usually wanted, and these evaluation schemes are usually, both of them, which I introduced, are penalizing for those. So you only get points for one detection, but every duplicate detection after that will be penalized. So this BBA, bounding box aggregation methods, can be used to either eliminate or merge most of the overlapping bounding these prediction boxes. So there are 2 ways. Basically, the idea is to get rid of most of the boxes here. So you can either eliminate them, try to eliminate them, or you can try to merge them together. It can be thought of kind of a clustering problem, and you can think of these boxes as 4D data points if you like. But the problem here is that, how to do this BBA, which is most suitable for C-SAR-APD. This is and my argument here is that the C version here might be better for the visualization's sake, and there are also some other reasons why you should do it like that. But before we go to how that, let's discuss about the non-maximum suppression way of doing that, which is this BBA, which is this is a traditional greedy algorithm that has existed already for 50 years, and it's eliminating these boxes. And it's a de facto method, so it's used widely in many modern object detectors, even though it's so old, but it still works really well, especially in these VOC 2000 and MS COCO object detection benchmarks, which emphasize different stuff than C-SAR-APD. So they want this exact delineation of multiple objects, and usually the objects are much larger in size than in C-SAR-APD. But the idea of NMS is just leave one box with the maximum confidence score. So everything around the, so to say, maximum is eliminated. So in an ideal case, you are left with only one box, which is the correct detection. But of course, this problem gets tricky when there are many objects which are overlapping, as you can see in this B image. All right, but there is a problem with this type of post-processing, that this emphasis on exact delineation of each individual objects can produce, so to say, poor results. And so because you are evaluating different criteria, so if you are failing to do this delineation, then you get poor results. But that's what your evaluation algorithm is saying. But if you don't care about that delineation of individual objects, then using that evaluation method is probably not the best one. But either way, even using our C-SAR-APD evaluation, you still run into this problem with non-maximum suppression, because it will still produce a lot of false positives by failing to eliminate some of the boxes. And using too much time on this can be detrimental to, like, it's not very useful to spend too much time on fine-tuning some IOU parameter in the NMS when you would be doing something that brings more value to the table. By the way, if you are interested in that evaluation schemes, like, you can even see the full pseudocode and all the details in section 3.3 in the thesis. Then there, of course, we are proposing our own method to do this PBA, which is called merging of overlapping bounding boxes. So the idea here is to simply merge all the overlapping boxes to one enclosing box, which kind of contains them all. And since we are not interested in this group separation problem or exact delineation, and what is the benefit of this approach to compare when we are using the C-SAR-APD evaluation scheme, is that instead of using, like, compared to this NMS and VOC 2000 combination, so you get increased precision and recall because we are evaluating a relaxed problem, and the generated performance metrics are, like, better aligned with the real life value in SAR operations. So this also implicitly helps researchers to focus on the important stuff, that when you see the metrics that they are improving, that metric is actually evaluating something that matters. And so the most visible thing is, of course, that there's better visual representation for these objects, less distractions, less clutter. It helps to reduce the information overload for the already exhausted visual analyzers. And another nice property of this type of post-processing is that you don't need to care about a couple of hyperparameters, which would be needed to tune. You would need to tune these if you want to separate the objects inside a dense group. Yeah, it's a kind of heuristic method anyway, and if we just overlook this whole group separation problem, then we can just use some pretty generic values for this, and it doesn't. Their contribution is not affecting much to the overall performance. Okay, so then we should discuss how did air come to life, so to say. There are 6 major experiments that I conducted to improve the performance of the vanilla RetinaNet detector. And the first one is hyperparameter search. By the way, I'm not going to too much detail here. You can read all about it in the thesis chapter 5, but I'll just give an overview here quickly. So selecting the best combination of hyperparameters, trying various combinations and checking what is the validation performance, and selecting the model which has best validation performance, and selecting, of course, those hyperparameters values as well. The theme here is pretty similar in all of these experiments, that we are checking some performance metric and selecting based on that. But in backbone selection, we are choosing the correct CNN backbone for the object detector. I'll be getting back to that later, quickly, soon. And Ablation Study is a more general collection of tricks that I tried to improve test performance. A funny thing that this random trial experiment is actually so significant. I just tried different random generator seed values and kept everything else fixed, and apparently it affects the performance a lot. And the fifth experiment is so-called model calibration study. So calibrating this confidence score threshold parameter turns out to be very important if you are using the VOC 2012 and NMS post-processing in your object detector pipeline. The sixth one is something called tiling performance study. I didn't discuss this yet. Because of the high resolution of those heritable images, you need to split the image into tiles, because the whole 4K resolution image doesn't necessarily fit into the GPU memory. And believe me, I used 32 gigabytes of GPU memory. That's a lot of GPU memory, and still it doesn't fit into that memory. So you need to cut it into parts and do this detection to those parts separately. But then I tested how this grid density or into how many parts exactly you split it, how it affects performance, or like the inference speed or the accuracy of the object detector. All right, let's look at some of these experiments a little closer. One fundamental question in machine learning is, how do you represent features? So in this backbone architecture selection study, it means how do we select the CNN backbone, basically, which is the feature extractor of the object detector. Here are the results. We are trying 8 different CNN backbones, and the winner is clearly here, the ResNet 152, based on the test set average precision metric. Another strong competitor is this VGT16, and it's actually performing better on the train set. However, it could also indicate some overfitting is happening. Interesting thing is that these champions of the ImageNet classification challenge, which should be more sophisticated than ResNet or VGG, they are actually performing like significantly worse on this heritable data set. So apparently they might be too specialized for this C-SAR-APD task. So, okay, let's pick this one. Then we have a lot of these different miscellaneous studies here listed, conveniently collected into this one table, and we call it just Ablation Study. Just any trick we try this one ablation. It's a term borrowed from the neuroscience, but let's not care about that too much. Then the first row here is the interesting one, that we are not using any other modification than this ResNet 152 backbone, which was selected in the previous study. But now other modifications are done to the vanilla RetinaNet detector, and the test performance is quite poor. But the moment we start to calibrate the sampling grid, basically, which are something called anchors, the image sampling grid, we tune it for small objects, we get a tremendous boost, like in this average precision metric. Or you could say that first we detect almost nothing, and after the calibration of these parameters, we detect half of the people. So that's quite a big improvement. Then, of course, the image tiling scheme, which I talked about, is also very significant. It improves performance tremendously because we can use the full resolution of the image instead of resizing the image, because you need to fit it into the GPU memory. And if you resize, you lose some of the pixel information. That's quite intuitive. Yeah, the E here, which has, okay, we are not even using all of these ablations because they are not improving performance. So we keep this E ablation for all of them. And it's about data augmentation, which also was designed in this thesis for C-SAR-APD purposes. And we use random geometric transformations and color operations online, like during the training to the input images. So we get much free data by doing this, so to say, by rotating the images or changing the brightness. And apparently that's something you need to teach to the network by yourself. It's not something it just magically learns. And also we use transfer learning for all of these backbones. They were already pre-trained on ImageNet. So that also helps with the little data we have. Okay, let's highlight this random seed study because it's so tremendous, this effect that you get like almost 5 points of AP just by choosing the correct random initialization. That's impressive or depressing. I don't know which one is it, but also we lose some precision in the process. So we need to do this score threshold calibration as the last step to redeem some of the lost precision here. So without losing too much recall. So this is a very important step. This was, by the way, all evaluated on the VOC 2000 evaluation. So, and let's discuss a little bit about this calibration study because it's giving so much characteristics about how the evaluation schemes and the BBA work together. And apparently, so here are the score threshold is on the x-axis, and so it can be something between 0 and 1. And on the y-axis, there's precision and recall. We are using the discussed evaluation methods and the 2 discussed BBA methods and comparing them against each other. And it's quite visible that actually if we switch just the evaluation scheme and keep NMS, there is not much difference here. But as the moment we switch to using MOB, then the precision it starts to be much less sensitive to the choice of score threshold parameter. And that's a nice property because we can just choose this 0.05 here to get the maximum recall, and we still get very good precision. But we likely don't want to do it with the NMS because then we would lose so much precision that it looks bad on the paper. So this is the effect of using our methods. All right, so we have some results here, then it's time to put them into some kind of context. So how do we compare to the state of the art in this problem? So here are the results. We have, again, 2 evaluation schemes here. The reason is that we can't really directly compare to others with our own evaluation. They are not really comparable. And the reason we defined these evaluation schemes in the first place is that this Heridal dataset does not really specify it properly. So there is some ambiguity in how these results were obtained or calculated, and it's not clear whether these results are really comparable or not. But because this is so widely used, we just assume here that they evaluated their results using this evaluation scheme, more or less. And let's not discuss all of this. You can read this again from chapter 5 in thesis, the full analysis of these results. But let's take some picks here. The faster RCNN, which is a very popular object detection framework, it works very well out of the box. There's like not too much modifications done. Okay, they did some. They also used tiling and used a different backbone than we. And by the way, this ATI is average time per image. in seconds. And they are very fast, they have better recall than we get. And then there is like this AP metric is also very good. And then there is this two-stage multimodal CNN, which gets the best recall out of all of them. They only miss like 5% of the people in the dataset, which is really commendable. However, the model is really complex. They use 4 different CNNs, like a kind of ensemble methods to come up with. So they use 10 seconds per image, which is quite slow, but it's still faster than humans. And they use actually 4 GPUs to produce this, or actually it's not clear how the hardware setup was used, but at least they reported 4 GPUs. So here's our results here with the NMS post-processing, and clearly we outperform all the other competitors in precision, and our recall is not falling too short of them either, and we are much faster than this two-stage multimodal CNN, which can even mean hours of difference in the analysis time when you have like 2,000 images to look through or something like that, which can happen during real SAR missions. All right, but then we also have the C-SAR-APD evaluation, which is here because, well, first of all, we want to see what the change of the evaluation affects. So there's like little improvement in speed, improvement in all of the metrics, and the speed stays the same. And oh yeah, well, because of the NMS, but with MOB it also stays the same. So it's clearly that relaxing the bounding box alignment requirement gives some benefit, but it's not the major thing here. But the moment we actually start to exploit this group relaxation, we don't need to separate each group. We get a huge performance bonus here, indicating that this separation of tight groups is actually what's bottlenecking the performance on this test set. All right. Then some example predictions. There's the NMS version. Here's the MOB version. And from the SAR point of view, it could be argued that there's little difference between the 2 images here, or like the predictions produced. Then, of course, we have the typical single-person scenario. Again, not much difference. You just get a little bit looser box with MOB. So, yeah, so the main benefit of using MOB on Heridal is that you can group the labels, and without the nice thing is that you don't need to define new ground truth labels. You can just use the existing ones and just evaluate them differently and to get results that better align with the problem requirements. All right, so to conclude this thesis presentation, we state that there are 4 main contributions that were made. The first one is the formulation of the C-SAR-APD problem, which has been largely left out from the original Heridal paper. So we give some definition for the problem and for the evaluation criteria. How do we rank the solutions? Also, we gave a baseline for human performance. So how well humans do this task. So clearly, almost all of the detectors here are performing better than humans, especially if we look at the last line here, we are like 30 times faster, or at least an order of magnitude faster than any human, and we are performing almost at the rate of the best human observer that I saw in those studies. So it's very commendable. And it's also consistent. We don't need to, the algorithm doesn't suffer from fatigue. So it doesn't matter how many images there are, which is really nice result. The second contribution is that there is a lot of these studies that we collected. So surely there is some insights to draw from those. You don't need to do those studies from scratch. So you can take some hints from this extensive list of results that were provided in this thesis. Then naturally, we need to highlight that the air detector achieves state-of-the-art performance on the Heridal, this difficult Heridal benchmark, especially in precision and speed. and the recall is not falling too short of the other competitors either. We also need to highlight here that the precision can be very significant if human and computer are interacting in this inspection task, because of course it's important not to miss anybody, but just producing too many false alarms if you have low precision is also can be detrimental, because the human inspector might get irritated or frustrated with all the false alarms and start doubting the algorithm altogether. So it's beneficial to have that nice precision. And the last thing is this mob algorithm, which enables like reliable approximate object localization in APD tasks. The reliableness comes from that you don't need to put the score threshold so high to perfectly separate the groups. So you can use lower score thresholds and without maybe suffering from precision declination. Also, the bounding boxes are visually looking really pleasant. So it's nice to analyze those kind of predictions instead of using the traditional NMS to do that, which produces a lot of clutter. All right. That concludes the thesis presentation. Thank you for listening. And now is a perfect time to ask questions if you have any.
Can I ask a question?
Sure, go ahead.
Yeah, I was thinking about when you create these detection boxes, is there any limit to how large they can become? Because, you know, I don't know, well, let's say there was a festival or something and there's huge amount of trash in a very large area on the ground that creates all kinds of detected things by this algorithm. Can it be like, okay, they are like a few meters apart for a very large area, so let's say it's like 100. Can it create, is there any limit to how large the detection box can become in this algorithm? Like, can it be like 100 meters by 100 meters?
Yes, you mean actually the post-processing algorithm. So does it have any limit to? Yeah, it too has a limit actually. Well, here I'm showing actually what the evaluation algorithm is accepting still. If you have about this A size humans, then this B size would be, they are all dependent on what IOU threshold you select. So you get kind of maximum box that is the maximum size for the box, and then also it can move around so that it still has the maximum overlap between the person. So you can basically this size box inside this C area is accepted by the evaluation. And you also can limit the size in the mob algorithm, that what is the maximum size for the output boxes. So it does this kind of subdivision of the box clusters. And you can, if you exceed the maximum area for the box, you can give it as a parameter.
Okay, so okay. Well, I guess that answers my question.
Yeah, but there is a maximum for both the evaluation and the mob algorithm. You can specify which is the maximum size of box.
Does it automatically subdivide those kinds of, if you give that maximum size of the box, is there any problem for it to create like if this is the largest size of the box, but you know the area in which there are detected sources a few meters apart is very large, does it create many boxes of the maximum size, or is there some kind of that kind of thing, or does it just create one largest possible size of box for that area?
Well, actually what it does, if like it goes for the maximum size of box with what you can get by selecting all the overlapping boxes, and then it does this heuristic splitting of the box inside like the maximum coordinate axis direction. You just put it in half, then you check whether the box is still like exceeding the maximum area. And if it's not, then you just keep those two boxes which are like the big box split in half. And if not, you consider this subdivision until you don't no longer exceed the box size, the maximum box size. So
Okay.
you kind of
Nice.
do some recursive splitting there.
Nice.
All right. Any other questions? It's time do we have left? Like 5 minutes. All right. So if there are no more questions, I'll thank you once again for joining this presentation. And hopefully you found something valuable information out about it. I'll be publishing my thesis work shortly, so be aware of that. So if you want to check these details from the thesis, it will be public document. So also I will be publishing a conference paper, hopefully during the next year or something. So you might also want to look out for that. All right. I guess this will be the end of the presentation.